Hello everyone. Today I'm going to talk about discrete distributions. Specifically for this section, we are talking about AB0 class. Before we get to the detail, we just want to talk about some things that we should know. That the PMF will be denoted as Pn in this section. This will be consistent with the exam table. So basically, probability of m equal small m is noted as Pn. And in this section, we will discuss each member of the AB0 class, which includes Poisson distribution, binomial distribution, Bernoulli distribution, negative binomial distribution, and geometric distribution. So what's an AB0 class? The AB0 class distributions are defined by the following property. Pk over Pk minus 1 will be equal A plus B over K. K will be 1, 2, 3, etc. So if we move K to the left side, K times Bk, Pk over Pk minus 1 will be equal Ak plus B. We can think of A as a slope if we plot K as the x-axis and K times Pk over Pk minus 1 as the y-axis. For each of these distributions, we can find out A and B. For example, for Poisson distribution, A will be equal to 0, B will be equal to lambda. This table gives you the A and B for each of these distributions. And expected value of m will be equal to A plus B over 1 minus A, and variance of m will be equal to A plus B over 1 minus A power square. Now let's review the Poisson distribution. Let n follows the Poisson distribution with mean lambda. Then we know n has the following probability mass function. Pm will be equal to e to the negative lambda, power of negative lambda, and times lambda to the power of n over m vector. One key property of the Poisson distribution is that mean equals its variance equal lambda. The sum of independent Poisson random variables is a new Poisson random variable. This is expressed as follows. If n1 is a Poisson distribution with lambda 1 as the parameter, n2 is a Poisson distribution with lambda 2 as a parameter, and so on and so forth. Then when you add them up, n equal sigma ni, I is from 1 to k, then this n will follow a Poisson distribution with mean equal to the sum of the mean of the k Poisson random variable. Basically, you're adding up lambda 1, lambda 2 to lambda k. This will be the parameter for the new Poisson distribution. The next distribution we are going to talk about is binomial distribution. A binomial distribution with parameters m and q means there are m independent trials. For each trial, an event of inches occurs with probability q. Let m follow a binomial distribution with parameters m and q. Then n has the following PMF. Pn would equal m, choose n from m, times qm, q to the power of m, and times 1 minus q to the power of m minus m. The mean of this n is mq, variance is mq times 1 minus q. Binomial distribution, if we think of a real life example, would be if you flip coins 3 times, how many times you will get heads and how many times you will get tails. So the number of, if you flip 3, and we are asking probability of n equal to probability of 2 twice you will have had, then your probability of P2 will be equal choose 2 from 3 times half to the power of 2 and another 1 minus half to the power of 1. In this case, Q and 1 minus Q is both half, but in other examples, Q and 1 minus Q could be different. Similar to Poisson distribution, the sum of independent binomial random variables with the same parameter Q is a binomial random variable. In this case, if Ni is followed by binomial distribution of MiQ, and N is equal sigma Ni, I is equal 1 to K, then N will follow binomial distribution with first parameter is sigma I is from 1 to K, and Q is still KQ in this case. A Bernoulli distribution is a binomial distribution with m equal 1, and the expected value is just Q because the probability of things happening is equal Q, and probability of things not happening is equal 1 minus Q. And so variance is just Q times 1 minus Q. The sum of M, IID stands for independent identical distributed. So the sum of M, IID Bernoulli random variables follow a binomial distribution with parameter M and Q. In this case, we are saying N1, N2, and Nm all follow Bernoulli distribution Q with parameter Q, then N is equal N1 plus N2 plus Nm. Then N will follow the Bernoulli distribution MQ. Negative binomial. First, we want to understand what's negative binomial distribution. Negative binomial distribution expresses the number of failures in a sequence of independent identical distributed Bernoulli chart before a specified number of success R occurs. So here n is the number of failures. It could be 0, it could be 1, it could be 2. Beta here is not defined the same as probability exam. In the probability exam, beta is defined as the probability of success, but here we define probability of failure to be beta over 1 plus beta. So if I say let's play ping pong, if I want to stop, if I won 3 games, if I win 3 games, then R is 3, R equals 3. How many times do we have to play before? How many failures I will attempt before we stop this? The number of failures is m. So the total number of game we play will be m plus r. Then among these m plus r games, the last one will be, okay, let me see. M plus r games. But the last one is always winning, so we have to minus this one. Then among this n plus r minus 1 gains, I have to choose n gains that I will fail. And this probability would be, probability of failure is 1 plus beta. So if I fail n times, you have to raise to n's power. Then after that, you will have 1 plus beta, which is success. That will be r. So this is this formula. This is more intuitive than this formula that will be given in the exam. But I think if you understand this negative binomial distribution, it's easier to remember this formula. And And from there, we also know that the mean is R times beta. And variable will be R beta times 1 plus beta. Similarly, the sum of independent negative binomial random variables with the same parameter beta is also a negative binomial random variable. And the new R will become the sum of all Ri together. Now let's talk about geometric distribution. A geometric distribution is a negative binomial distribution with R equal 1. The PMF, mean and variance, are simplified to this. Pm would be beta to the power of m over 1 plus beta to the power of m plus 1. This is just basically, this is basically from previous you have this is m times number of success is 1 plus beta. This is basically the same as this. And EM, expected value of m will be beta. Expected variance of m will be beta times 1 plus beta. Once you understand previous negative binomial, it's easier to understand this geometric distribution. Geometric distribution has a very special property, which is memoryless property. To understand this, we need to take a look at these formulas first. First, pk over pk minus 1 is beta over 1 plus beta. This was given. Then, second, we want to ask the probability of p m greater than k, which just means you have to sum up all the pk and pk plus 1 plus pk plus 2. We know that the pk is number of, if we consider as a number of failure before number of success, one success, number of success is 1 plus beta. Number of failure is 1 beta over beta, 1 beta over 1 plus beta to k. So, and we can see that between pk and pk minus 1 is just a factor of beta over 1 plus beta. So if we remember this, first one is pk, the next one is just 1 plus beta, 1 plus beta. And the second one will just be beta, 1 plus beta square, so on and so forth. Then in this case, we can utilize the series, the formula for the series, geometric series, where it says a1 plus a1q plus a1q squared all the way would be a1 1 minus q 1 minus q. In this case, if this is infinity, then it really just becomes a1 over 1 minus q. So if we apply this here, apply this formula to this, it will just become, first pk is 1 plus beta over 1 plus beta to k, and this part will just become 1 minus q. 1 minus q, in this case q is beta over 1 plus beta, and it will become 1 plus beta. So this and this will cancel, then essentially you will get this beta. So the final answer will just be beta over 1 plus beta to k to the k's power. Now let's talk about a memoryless probability. If we are saying probability of geometric distribution is memoryless. It means that P probability of m greater than m plus k, given that m is greater than small m, would be the same as the probability of m greater than k. Now, this first one is we can calculate the probability of m greater than m plus k will be beta 1 plus beta m plus k over this is beta 1 plus beta m. There was a 1 plus beta 1 over 1 plus beta, which will be cancelled off, so we don't need to worry about that. But this can further be deduced as beta over 1 plus beta k, which is just the probability of m greater than k. So this is saying the probability geometric distribution has the memoryless probability property. Now this slide tells us how geometric distribution is connected to negative binomial distribution. So the sum of RIID geometric random variables follows a negative binomial distribution with parameter R and beta. N1, N2, NR if it's following the geometric distribution with beta as the parameter, and N is equal to N1 plus N2 till MR, the M follows negative binomial with the parameter R and beta. As stated earlier, the geometric distribution has the memoryless property. That means for M follow geometric beta, M minus D, given that N is greater than D, follows the same distribution as M. Then M minus D, given N is greater than D, would follow the geometric distribution beta. The memoryless property also implies the following. Expected value of n minus d, given that n is greater than d, would be the same as expected value of m, which is beta. Variables of n minus d, given that m is greater than d, is the same as variable of n, which is beta times 1 plus beta. Probability of n minus d equal a, given that n is greater than d, would be the same as probability of n equal a. This is just what we talked about in the earlier slides, except that earlier slide we use k rather than a here. Now let's look at some examples. For a discrete distribution in the AB0 class, you are given the probability of 4 claims is 0.066116, and the probability of 5 claims is 0.068761. The probability of 6 claims is also 0.068761. Determine the probability of no claims. So to solve this problem, we just need to figure out the parameter first. To figure out parameter first, we want to utilize what we learned before, this formula. So P5 over P4 will be A plus B over 5. It's point, we can carry as point that. And again, P6 over P5 will be A plus B over 6 will be 1. From these two, we can calculate A is equal point A and B is 1.2. So because A is greater than 0, we can also tell this is a negative binomial. A is greater than 0, so it's negative binomial. And in this case, then we will know A is equal beta 1 plus beta 0.8. So we can get beta is equal beta is 4. B is equal 1 minus A will be 1.2. So we can get R is 0.2. Then the probability of no claim P0 will just be no claim, means probability of this. This will be this to the power 2.5. That's 0.789. So first we use this formula to figure out A and B. Then from here we can tell this is a negative binomial. And from this we can further determine beta and R. Once we have a beta and R, we can use the formula of P0 to calculate the probability of no claim. Now let's look at example 2. For a distribution from the AB0 class, you are given that P2 is equal to this 0.03072, P3 is 0.04096, P4 is 0.049152. Calculate the mean of the distribution. First, again, we use the same P3 over P2 would equal A plus B over 3 equal this, and the P4 over P3 would equal A plus B over 4, 1.2. Then from these two, we can get B is equal 1.6, A is equal 0.8, which is greater than 0, then we can further say it's MB, negative binomial. Then B is equal R minus 1A, and A is equal beta 1 plus beta. So from here we can get beta is equal 4 and R is equal 3. Then the expected mean EM would just be A plus B over 1 minus A. So we really don't even need to calculate the beta and R. We can just get it directly equal 12. But also you could use En equal R beta to calculate 3 times 4 is the same. So either way it's fine.